Now it is the turn of vectors to be discussed. So what we will be discussing now is vector. Vectors are characterized by the fact that they have magnitude, also called modulus, and this in fact is the scalar part. So it is also called the scalar part. And vectors have one direction. So vectors are physical quantities that possess magnitude and one direction, and further they obey rules of vector algebra. And next, let us illustrate the rules which vectors respect. Which vectors can be added? Like vectors can be added. So like vectors can be added or subtracted. For instance, this is a force F1, and to it we can add another force F2, and we get a resultant force vector F. But to a force vector F, can we add a momentum P? This makes no sense. This is meaningless. Another rule is that vectors can be multiplied by scalars. Let me now mention the laws of vector addition. Vectors obey number 1, triangle law of vector addition, and parallelogram law of vector addition. And in fact, the two laws are same. One can be derived from the other. The triangle law says that if we have a triangle, say A, B, C, then we can construct or think of the vectors AC, CB and AB. And if we construct vectors in this way, then the following relation exists: AC vector plus CB vector is equal to AB vector. So this is called triangle law of vector addition. Now if we construct the vectors in a different way, this law will change. For instance, the same triangle can be looked upon as made up of these vectors AB, BC and AC. Now in that case, the triangle law of vector addition would be AB plus BC equal to AC. and the two are identical, because if you shift BC to that side, it will become CB, and we end up with AC plus CB is equal to AB, which is in fact this law. So you need not memorize how we are taking the vectors. You can take it in any arbitrary fashion and then write down the triangle law of vector addition looking at the triangle, in which you have put the vectors in whichever way you like. Now comes the parallelogram law of vector addition. So you construct a parallelogram which is A, B, C and D, and this is the diagonal. Now we can construct the vectors in the following way. You take AB, you take AD, and then vector AC is the diagonal. Then according to parallelogram law of vector addition, the diagonal AC is in fact the vector sum of AB and AD. And this is in fact identical to the triangle law because of the simple reason that you can translate these vectors, and vector AD, it being a parallelogram, is identical to vector BC. So instead of AD we can write vector BC, and therefore this parallelogram law takes this shape. So AC is equal to vector AB plus AD, but instead of AD we can write vector BC, and this is nothing but triangle law because it follows from this triangle. So these two laws are essentially the same. Let us mention the rules of vector algebra. We think of three vectors. One is A vector, one is B vector, one is C vector. Now vectors obey associative law. Which tells us how we can associate these vectors and form meaningful expressions. For instance, we can add B and C, and the sum which we get can be added to a vector A. So we have this thing. Alternatively, one can add A and B first. So we have A and B, and to it we can add the remaining vector C. Now according to associative law, the two modes of association lead to the same result. So this is what we get. Let us think of two scalars x and y. Now we can form the product. We can multiply A by y, and therefore we have this thing. And then let us multiply this product with x, and this is the final product which we get. We can also take the product of the two scalars first and then multiply A with it. Now according to associative law, these two are same. So associative law in fact tells us how we can juggle with vectors, how we can associate them to form meaningful expressions. Let us now mention another important law which goes by the name commutative law. Now earlier we saw that scalars commute. Scalars commute means we can write x plus y as well as y plus x. These two things are same. X and y product is equal to y and x. So we say that the scalars x and y commute and they are C numbers. Let us consider the vector A first, and to it we add vector B, and someone might start with vector and to it he or she may add A, and according to this law the two are same. We can multiply x with A, and so we have xa, or we can write A first and then write x later. Now the two things are same. So vectors obey commutative law, and this expression is very important because this shows that scalars can be put anywhere. It can be put first or it can be put later. So scalars can be pushed in at any place according to our way of writing, according to our wish. Another law which vectors obey is the distributive law. Which tells us how to distribute the vectors. Suppose we add x and y, and then with it we multiply a vector A. Another method is multiply x with vector A, multiply y with vector A, and then take their sum. And according to this distributive law, the two are essentially identical, they are same. Or we may combine A and B, and therefore we have A plus B, and then we can multiply this sum with x, x being a scalar. Or another way is we can multiply A with x, multiply B with x, add them, and according to this distributive law the two are same. So these are the laws which vectors respect, and we have studied them in details. Let us now consider some examples of vectors. Consider a particle moving from point A to point B, which means that the particle has been displaced by an amount AB in a specific direction, which is from A to B. So we can construct a displacement vector which is vector AB, and let us write it vector R. So displacement is a vector because it has a magnitude AB, this distance, and because it has a direction, one direction from A to B. Again, velocity is the rate of change of displacement. So velocity, which we denote by vector V, which is vector dr dt. ddt is a scalar operator and vector r is a vector which is called displacement, and dr dt gives us velocity. This also is a vector because it has two parts. One is the magnitude part, the speed part, and the other one is the direction part. Next is acceleration. Which is vector A. Let us denote it by vector A, which is the rate of change of velocity. And the double derivative of displacement. So these are examples of vector quantities. Also we can think of momentum, which is vector p and which is the product of mass and velocity. We can think of force, which is a vector quantity denoted by vector f, and force is mass into acceleration, which is the famous Newton's law, and we can write it or express it in the following way. So these are examples of vectors. Also, electric field is a vector quantity. We denote it by vector E. Magnetic induction is a vector quantity. And there are specific expressions of these things which we will not study at present, but we will take up later. And there are so many examples of vector quantities. Let us have a relook regarding how we specify a vector. Vectors are expressed in the following way. A vector is a combination of two parts. One is the modulus part or the magnitude part, or what we call the scalar part. The other part, without which we cannot think of a vector, is the direction part. So there are two parts. One is scalar part, the other one is the direction part. Now scalar part is expressed by a numeric, and the direction part is expressed by unit vectors. So this is how we can write down a vector. So let us consider a vector A. The scalar part, let us write it to be A, that is without this arrow sign overhead, and the direction part is denoted by writing A, and over it we have to put a cap sign or hat sign. So this is how we express a vector. And here this A is in fact the modulus A or the magnitude A, and this unit vector A cap is therefore vector A by A. So this is how we can express the vectors. Also, what will be the modulus of the unit vector? The modulus of unit vector is, as the name implies, unity, and we can prove it by taking the modulus of A cap. So unit vector is indeed of unit modulus, hence the name. So accordingly, displacement can be written as r into r hat. Velocity can be written as v into v hat. This is the scalar part, modulus part, which is also called speed, and this is the direction part, which when associated with speed it becomes velocity. Acceleration vector has two parts, a hat being the direction of acceleration, a being the magnitude of acceleration. Momentum part, p into p hat, and here p is in fact m into v, v being the speed. Force can be written as F into F cap. The electric field similarly can be written, and magnetic induction can be written as B into B cap. Next, there are two types of vectors. Having units, first type of vector has unit. For instance, velocity v is 30 meter per second, say. So there is a numeric and there is a unit, and this v is the magnitude of the velocity vector. So this vector has a magnitude and a direction, and the magnitude is described by a numeric associated with a unit. And we have vectors which have no unit. And they are none other than the unit vectors. Because the unit vectors have unit magnitude, they have direction only, they possess direction only, and they have no unit. For instance, the unit vector along velocity can be denoted by v hat, and it is given by the velocity vector divided by the modulus of the velocity, which is written in this way. Let us next come to a very important aspect of vector. How would we specify a vector? So, specification of a vector. In other words, let us ask how many components are needed for description of a vector. Let us give the answer directly. The answer is, in d dimension, we require d components or numbers. Let us illustrate this point. First, let us think of one dimension. So, this is x-axis denoted by x cap or x hat. Suppose this is the origin, and we consider a point P here, and the coordinate of the point P is x. So this distance is x, and we can write it as vector OP is equal to vector R. This is vector R, and this is actually equal to x into x hat. So this is how we write it. It is very clear that we require one coordinate or one number or one component for description of this vector, and that number or that coordinate or that component is x. Here vector R is the displacement vector or the position vector, or it is called the radius vector or the displacement vector. So in one dimension we need one component only to specify a vector completely. Let us think of two dimension now. In 2D we construct two axes. One is x hat, and perpendicular to this axis we think of y cap. So x cap and y cap define a two-dimensional space, and in this space let us consider any point P. Now how will you express this vector OP? The projection along x-axis is x and the projection along y-axis is y. So this distance is x, this distance is y, and accordingly the coordinates ascribed to this point P in 2D space is x, y. And we write OP as, this OP is actually the position vector R, the displacement vector R, or the radius vector R, and this OP is written as x cap plus y hat. Now how many coordinates are needed to describe the point P? To specify any point in 2D space, for instance this point P, we need two coordinates. Or two numbers or two components. And what are the numbers or coordinates or components? One is x and the other is y. So in 2D we require two components, and we needed one component in 1D space. Let us think of a 3D space. A 3D space is an extension of 2D space where we put a third coordinate. So suppose this is x-axis, this is y-axis, and this is z-axis, and any point in this space is P, then this is the radius vector or position vector or displacement vector of P, and this vector OP is described as x cap, y cap, z cap, where the projection of P on x-axis is x, the projection of OP along y-axis is some distance along y, which is y, and the projection of P along z-axis is some distance from the origin along z-axis, which is some number z. So to specify a point in 3D space, we need 3 coordinates. Or 3 numbers, or what we call 3 components. And they are x, y, and z. So it is clear that in 3D space we require 3 components, 3 numbers. In 2D we require 2 components, and in 1D we require 1 component. So in d-dimensional space, or in d dimensions, we need d coordinates or d numbers or components. So let us recapitulate. In d-dimensional space, we require 1 coordinate to specify a scalar, but d coordinates to specify a vector.